Hi class, this is a second video on electromagnetic waves, and in this video I'm really going to focus in on the relationship between a wave's frequency and its wavelength. You'll remember that electromagnetic waves can come in any wavelength imaginable. We use the letter lambda, that's the Greek letter lambda, to describe the wavelength, and the wavelength is the distance between successive peaks of the electromagnetic wave as it propagates forward at the speed of light, and the frequency of the wave is the rate at which the wave wiggles up and down as it propagates forward through space. We're going to arrive at a mathematical relationship between these two properties such that if we know a wave's wavelength, we can calculate its frequency and vice versa. But first we can just look at it qualitatively by looking at these two cartoons of a pair of waves. This is a wave with a shorter wavelength, and this is a wave with a larger wavelength, so that we can compare them to each other. We want to keep in mind that all electromagnetic waves travel at the same speed, which is the speed of light, 300 million meters per second, or in scientific notation, 3 × 10⁸ meters per second. And what we're going to find is that waves with a smaller wavelength, like this one, is going to have a larger oscillation frequency, meaning that as it propagates forward, it wiggles up and down more rapidly, and vice versa. Waves with a larger wavelength, like this one, it'll have a smaller frequency, so it'll oscillate up and down more slowly. And you can already kind of visualize it right here. Imagine that these two waves are passing by us at the same speed, and you observe these two waves go by. Well, you're going to observe this wave wiggling up and down more rapidly as it's passing by than this wave with the longer wavelength. And one analogy I sometimes use, which is a little ridiculous, but I came up with this during teaching one of my previous astronomy classes. Imagine you've got an animal, like a little animal, like a small dog or something, like a chihuahua, for example. And imagine you've got a really big animal like a giraffe. And imagine that they're running next to each other at the same speed. So the chihuahua would be like the little, with its little legs, each time it takes a step, it has a very small wavelength. And the giraffe, with its really long legs, it would have a very long wavelength. Well, if they're both traveling at the same speed, the only way that the chihuahua is going to keep up with the giraffe is if it's taking many more steps per second than the giraffe is. That's the only way that with its smaller step size, it can keep up with the giraffe. Well, with electromagnetic waves, they all travel at the same speed. So an electromagnetic wave with a smaller wavelength is going to have to complete more cycles of oscillation every second in order to keep up with an electromagnetic wave of a longer wavelength. So I hope you enjoyed thinking about that. Here is the mathematical relationship right here. The speed of light, which we give the special letter c to, is equal to the wavelength in meters multiplied times the oscillation frequency in cycles per second, which we call hertz. That's the unit. I do want to point out one thing where I use different letters than what's in our textbook. We're using the textbook Universe. In the textbook, they use the Greek letter nu, which looks a lot like a V. And this is very standard in science and engineering to represent frequency with this symbol. But in astronomy, I think this is unnecessarily complex and sometimes can be confusing because it looks like a V. So I, for this class, prefer to just use the letter F for frequency, and I will stick with lambda for wavelength. So there it is. There's the starting equation. You can use a bit of algebra. You can divide both sides by F, and you can arrive at this equation, which is really the same exact thing, but here you've solved for lambda wavelength. So you can solve for a wave's wavelength by taking the speed of light over its frequency. And then you could do the same thing. You can divide both sides by lambda, and you can solve for the frequency is equal to the speed of light over the wavelength. So they're all the same equation. It's just that this one's set up if you want to calculate wavelength. This one's set up if you want to calculate frequency. And just a quick reminder on the units we use. We can use any of these units for distance, but we'd always want to convert them into meters before we plug them into that equation. And I described these units in the previous video on electromagnetic waves. And for frequency, it's all based on the hertz. And but we'll generally be talking about either thousands of hertz, kilohertz, millions of hertz, megahertz, billions of hertz, gigahertz, or trillions of hertz, terahertz. So let's just learn how to do this by doing an example right here. This is an array of radio telescopes. This is located in New Mexico. This is called the Very Large Array. And here's an image of a radio galaxy that it's produced. This looks at microwaves and radio waves. And this image in particular is looking at waves which have a frequency of 5 gigahertz. So 5 gigahertz is 5 billion hertz, 5 billion cycles per second. That's the frequency that these radio telescopes are tuned to. Well, let's calculate what's the wavelength of these electromagnetic radio waves or microwaves that this telescope is observing in order to produce this image of a radio galaxy right here. So the first thing that we'd want to do, if we want to go from this frequency and we want to convert this into a wavelength in meters, is that we would want to convert this first from gigahertz into regular old hertz. And that's pretty straightforward because you know that giga stands for billion, which is 10 to the 9. So 5 gigahertz is 5 times 10 to the 9 hertz. Now that we have the frequency in hertz, we can use one of our equations to solve for wavelength, and we'll want to use this one. So you just go back a few slides with those 3 equations, and this is the one we want. Because we know the frequency, we know it's an electromagnetic wave, so we know the speed of light is 3 times 10 to the 8th meters per second, and now we can calculate lambda, the wavelength. So here we go. You take the speed of light, 3 times 10 to the 8th meters per second, that's 300 million meters per second, and we divide it by 5 billion hertz, 5 times 10 to the 9 hertz. This is the first time we've encountered a problem where we have to do arithmetic in scientific notation, and this is how you do it. If you're doing division, so you're taking one number divided by another number, and these numbers are expressed in scientific notation. The first thing that you do is you take the little numbers out in front, in this case it's the 3 and the 5, and you do the division on them. So 3 divided by 5 is equal to 0.6, and then this is going to be times 10 to some exponent. The way you find out what that exponent is you take the exponent on top, which is 8, and you subtract the exponent on the bottom, which in this case is 9. So you have 8 minus 9, which is -1. So there's the answer. And when you take a speed in meters per second and you divide it by a frequency in hertz, what you get out is a wavelength in meters. So the 1/seconds from the top cancels out hertz. Those actually cancel each other out, and you're just left with meters for the wavelength. So we have 6 times 10 to the -1 meters, which we can express that as 0.06 meters, because 10 to the -1 meters is really 0.1 meters. It's 1/10 of a meter. So here we have 0.6 times 0.1, so we have 0.06 meters. 0.06 meters is equal to 6 centimeters. So when you look at this image right here, taken by this array of telescopes, these are radio and microwave telescopes, we can either think of it as being an image of 5 gigahertz electromagnetic waves, or we can think of it as being electromagnetic waves which have a wavelength of 6 centimeters. So I will post another video, in which case we're going to go through an example where I'm going to give you a frequency and ask you to calculate I'll give you a wavelength and ask you to calculate the frequency. So kind of like the opposite of what we did in this video.